last lecture, or maybe, can you put the Pune exam first? Huh? Let's just come back to your exam. I just put a correction so that you can get some feedback. And obviously we went not to, okay, that's this one. Not too used to do cross sections, something that was difficult exercise. I understand it. So actually we canceled, we didn't count any points on that. Because it was too much of a bridge, I think. So here was very easy. The distribution of earthquake delineates lithospheric plate boundaries, mid-oceanic ridges that are places of plate divergence, oceanic trenches along the Pacific marked by subduction, and orogenic belts characterized by diffuse crustal deformation. So if you have these three elements, then it's 3/3. What controls distribution of the edges of the oceanic crust? The edge of the oceanic crust decreases away from the mid-oceanic ridges, and it's older along passive continental margins. This distribution evidences the generation of oceanic crust by emplacement of mantle-derived magmas generated by decompression. This was not exactly expected, but I expand on that. In zones of plate divergence, as the asthenosphere diverges from the mid-oceanic ridge, it gets older and cooler and denser, and eventually subducts. So this was the basic. And here I changed a bit because the question was not so clear. So here I put the MOHO and the topography on the same, whereas I asked you to put MOHO and the lithosphere and asthenosphere boundary on the bottom one. But I think for the scale difference, it was easier to put the MOHO and the topography on the top one, and just the lithosphere boundary on the bottom one. So here the first thing was to identify a scale. So if you want to represent both topography and MOHO, then you need to be on 10 kilometer scale for one tick, and going down to at most 60 kilometers. So that's the first thing to realize. And then the idea was to show here that New Zealand is a small mountain with a small zone of thickened crust going down to 10, 20 kilometers, sorry, should be 30, it should be a bit more than that. This should be a bit more like that. Let's push more like this. And then a trench at the surface related to a zone of bending of the crust. So you have two lines here. It's difficult to see, but you have two lines. One for the topography, one for the MOHO. And they are very next to each other for the oceanic crust in the abyss at a depth of about 4,000 meters. And then in the ridge, you've got just a little bump, both in the MOHO and the topography. And you have the symmetric image in the Andes, but the difference with the New Zealand is that the crust is a bit thicker and the zone of thick crust is wider. And you have a crustal root beneath the high topography and a trench at the contact. And this relates to the lithospheric structure here. Then you need to change scale, go from 0 here to 600 kilometers. So every tick is 50 kilometers, 100, 200, yeah, that's it. So here it shows the lithospheric, asthenospheric boundary beneath the Andes at somewhere around 100 kilometers. Then here the subduction zone, where the plate goes down, the ridge, where the lithosphere thins, and the other side, subduction is going with another polarity. Okay, is it more clear now? Most of you didn't understand the question, so we didn't count any points on that. And I have to say, I was impressed by the way you write. And that's something that made me think, because students in France do not write that well anymore. In terms of syntax, sentences with a subject, a verb, a complement. It's just like SMS, no? Textos or rapid. I tell them, if you want to construct thinking, rational, reasoning, you need to construct sentences that are correct. It's not just word that I put like randomly, and okay, make your choice. No, I'm not going to make any choice. You have to express yourself in a way that is understandable. And you guys do it. I was really impressed by that. I'm not sure what is the problem with, I have actually some instance. I think phones and rapid communication. It's not to say that we're not going to use that rapid communication. It's good, in a sense, in a way, is a way to communicate easily. But in order to build a complex reasoning, that's not working. You need to elaborate. And I was really pleased to see that you can do it still. And I see that you take notes, and that's part of it too. You take notes, and I looked a little bit over your shoulder. You make sentences, and sometimes keywords, but I think that's the way to do it. Okay, so let's move to the last lecture that brings us to Precambrian cratons. So I'm going to be a bit shorter than what I was expecting. So most of the rocks look like that. And I guess some of you are familiar with these rocks. What they've been called grey gneisses, granitic gneisses, migmatites, and other high-grade rocks, charnockite. When we get into charnockite, grey gneisses, granitic gneisses, norite, and so on, that means we don't have a clue about the protolith. It's just rocks that are defined by mineral assemblages and reflect different proportions of pyroxene, garnet, plagioclase, some quartz. And if there's a lot of plagioclase and pyroxene, you call it a norite. If there's some garnet, you might call it a granulite. If there's lots of pyroxene, call it charnockite. But really, it reflects our lack of understanding of how they were formed. So it's justified to study these rocks as they form most of the cratons on Earth, right? And the main question we're going to address is how these rocks record some kind of geodynamics at the Archean Proterozoic transition, whether they form in a context of plate tectonics as Phanerozoic rocks, or if it was different, with maybe a stagnant lid with lots of gravitational instabilities in the mantle, or smaller plates in a more vigorous convection pattern or convection setting associated with a hotter Earth. And the questions we're going to address is how, when, and in which context did the first continental crust form? And then in order to address that, we need to compare, go a bit beyond what was treated by Nitin Karmalkar, go into a bit more into the guts of it, but it's basically what he exposed with the different type of crust and how it compares to the mantle. So in terms of mineralogy, I put here in green the main minerals of the mantle, in blue the ones of the oceanic crust, and in red the ones of the continental crust. We have basically olivine and autopyroxene for the mantle, cryopyroxene and plagioclase for the oceanic crust, and plagioclase K feldspar quartz for the continental crust. And that breaks down into chemical oxides, which indicates predominance of magnesium in the mantle, predominance of iron, calcium, titanium in the oceanic crust, and sodium, potassium, aluminium, and SiO2 in the continental crust. Note that there is silica in all rocks. It's the basics of all silicates, mineral silicates. But quartz and silica is expressed as a free phase only in the continental crust, very seldomly in the oceanic crust. And what we can see here by this organization is that the elements that are in the continental crust are not in the mantle. So there's sort of a mirror image of the continental crust and the mantle, and the oceanic crust is in between, has an intermediate composition. So it looks like the mantle is depleted in elements present in the crust. And that leads us to the mechanism that Nitin Karmalkar has mentioned, is formation of the crust by extraction of a magma from the mantle with incompatible elements that are and mobile elements that will be preferentially taken out of the mantle and form the crust. And these elements are these ones. all the mobile elements, the alkaline elements, potassium, sodium, somehow aluminum, and sodium, relative to calcium, iron, and magnesium. And of course, SiO2. And from a peridotite, magma extraction will lead to a basalt and to a granite. So we're going to expand a bit on that now. So today, the sites of cross formations are related to divergent plate boundaries. And here are the numbers in terms of how much plutonics and how much volcanics. So most of the magmatism is actually occurring at depth. And we only see as volcanics only part of it, maybe 20% of it. Most of it remains at depth. And the main site of magmatism is the ridge, the mid-oceanic ridges, and that dominates in terms of magma extraction. And then this is responsible for oceanic crust formation. This this oceanic crust is then expanded by oceanic plateaus that are more related to what we call hotspots. And there's also then volcanism and plutonism along magmatic arcs, along convergent boundaries that involve oceanic plates or oceanic plates and continental plates. So this leads us to some definition. We consider juvenile accretion as magmas are extracted directly from the mantle. This is called juvenile. And that's not to be confused with coastal reworking. Coastal reworking is when the crust is affected by deformation and metamorphism and maybe all the way to partial melting. So that crust was formed before but was then reworked. Coastal recycling corresponds to the return of the crust back to the mantle. So I'm going to let that just to say that we have specific signatures of magmas as a function of the geodynamic sites. Tholeiitic mafic rocks form in mid-oceanic ridges. Alkaline magmatism, Nitin has mentioned that, in oceanic plateau and oceanic and continental plateau. And along magmatic arcs, it's mostly calc-alkaline. And these are then associated with specific trends in the alkali SiO2 diagrams. The tholeiitic evolution of magma goes from low silica to high silica without much increase in alkalis, whereas the calco-alkaline, with the increase in silica, goes through increase of alkalis. And you can also have alkaline and hyperalkaline, which then are characterized by very low increase in silica, but a lot of increase in alkaline. Not going to go into the details, but just remember the name, tholeiitic calco-alkaline. What does that reflect? The basic idea is that this Si increase is correlated to a magnesium decrease, and this is called differentiation. And the main process that has been invoked so far for differentiation is fractional crystallization, going from a basalt to even a rhyolite. And the principle is here, and we mentioned that yesterday, as the first crystal that we crystallize in a magma don't have the same composition as the average magma. So the elements that are going to be trapped in these first crystals, as the crystals segregate from the magma, they will no longer be, these elements, they will no longer be in the magma. So the second minerals that crystallized after the first one, they will crystallize from a different magma composition and will trap different elements that will be then accumulated and will lead to a change in composition of the residual liquid, and so on, and so on. And this explains magmatic layering and also differentiation from more magnesium-rich crystals to more silica-rich crystals. So this we can explain with thermodynamics, but I'm going to skip that one. Do that adding one pole of chemicals, and here it's only binary reasoning. Here it's ternary reasoning, but it's the same idea. And by looking at the texture of the rocks, you can identify which one crystallized first, which will develop urethral faces, crystal faces, and the last one are the ones that are interstitial. And here, I'm going to go through that. You know. Here the idea we have climopyroxene, olivine, and plagioclase. So if you take we go from space here, and we reach that diagram at 1600 degrees, the first crystals that we crystallize are forsterite, and it coexists with liquid. So we are in the field of this olivine. And then the temperature will go down and then meet that boundary, at which point there will be crystallization of diopside, of anotite. Anotite, the plagioclase here, which will fill the gap in between the forsterite crystals, and then the reaction will go this way, the melt will decrease, and the last crystals to be formed will be diopside, filling up the space, interstitial space. So you can read the crystallization, fractional crystallization in the texture and compare with the thermodynamics. So at first order, the crust is layered with mafic rocks at the lower crust, more intermediate rocks, granodiorite composition in the middle crust, and granite and sedimentary rocks on top. And this might have been explained in the present day, according to the sites of geodynamic activity today. One possibility is that it's only fractional crystallization of magmas coming from the mantle, and then they first accumulate crystals that are more mafic, and then more felsic at the end. So it's a single process. And the idea is that there was some kind of magmatic column at the scale of the crust and the segregation of crystals and liquid. And that's mostly invoking juvenile magmatic accretion from mantle-derived magmas along magmatic arcs, and that might be a good model for that. In orogenic belts, the story is more complex. We have a pre-existing crust, so there it's mostly crustal reworking, deformation, increase in temperature, melting, and then melt crystal segregation. And so there's lots to, it's not as simple as in magmatic arcs, so we have a history, and it's a two-step story with formation of a first crust by some kind of differentiation at first, and then a second event during orogeny, which leads to increase in temperature, melting, and segregation of melt. Okay, that's for pretty much for the present day. So that's according to this setting. Today we can relate zones of magmatic accretion, crustal growth, and differentiation related to crustal reworking to different geodynamic sites. So how was it in the past? So in order to see if we can apply this model to the past, let's first look at the distribution of continents as a function of their age. And here the oldest one, so actually that's not the way it should be. Huh? You know, the legends should be the youngest one on top and the oldest one at the bottom. That's a map from geophysicists. So the oldest is here, but it's the merit of this map is that we can see more or less the different colors relative to each other. The youngest belt are in red, and the oldest is in purple, these ones. And blue is also old, Archean. And what we see, I produce a simplified version of that. What do we see in terms of distribution? The Archean, how is it related to the Proterozoic and Phanerozoic? What is the distribution telling us?
Can you repeat the question?
Yes. What is the relationship between the different colors, the different ages of the crust? Archean in burgundy, Proterozoic in blue, and Phanerozoic in red, in green. Sorry. Do you see the contact between
Archean is
less
less continuous.
continuous, huh? And is it in contact with Phanerozoic or with Proterozoic? Almost only Proterozoic. So you have a concentric distribution. It's very different from the oceans, where it's symmetric relative to the ridge. So what does it tell us? No, as a sign for coastal growth through Earth history. Well, the growth of continents was centrifugal, with first nucleus and then accretion of new crust around all the zones, right? That's the first order that we can see. And these old Archean and somehow, maybe we can extend that to the Proterozoic cratons, they are associated with blue zones in seismic tomography, which is fast, which means rigid and cold. So you see that the cratons are underlain by thick lithospheric roots. So now let's look at what we have as proposition for the growth and of the crust during the Earth history, mostly the continental crust here. So that's 4.5 billion years ago, that's today. And everything has been proposed on different type of reasonings. The first one was, okay, there's a lot of the crust has formed before the end of the Archean, right at the beginning of the Earth differentiation, at the time of nucleus or core mantle crust formation. And most of the continents, for Armstrong, proposed that they formed at the right beginning, and then all the rest of the history is reworking. Other people said, okay, no, it's the other way around. It's maybe a lot has been produced, but a lot has been recycled. Of the crust has been recycled in the mantle through erosion, sedimentation, and subduction of sediments. So then they end up with totally different histories. So I'm not going to build more on that. Condi, 98, did a first compilation of the zircon ages, and it leads to some kind of peaks. And he proposed him that instead of being sort of gradual, this growth of continent was discrete with peaks that corresponds to main orogenic belts and so supercontinent formation at different times of the Earth history. And that would be the last one is the Pangaea, but before you had the Rodinia, Nunia, and all these supercontinents have names during the Earth history. In order to understand growth and differentiation of the crust, we also need to take into account the secular evolution of the Earth, which is first recorded by mafic magmas and their magnesium content, which is a proxy for the amount of partial melting of the mantle. The more magnesium rich, the more the mantle has been molten, and the higher the temperature might have been in the mantle. And for example, if we take in the Archean, we had specific rocks that we're going to see just next. Komatiites are typical of the Archean and not found in the Phanerozoic, and they are high magnesium content, so this requires a higher temperature. So we can trace the evolution of the temperature as a function of time with, for example, MORB, the mid-oceanic ridge basalts. They require lower temperature as a function of their magnesium content. So this is a measure of what we call the mantle potential temperature, which went from 1600 degrees to 1300 today. And that is a record of progressive cooling of the Earth. Secular evolution is also recorded by metamorphic rocks. This is a compilation by Mike Brown, where you see in the past almost only these colors that corresponds to high temperature metamorphism, and very seldom blue colors that corresponds to the high pressure in the PT diagram. Whereas in the Phanerozoic belts, we have mostly high pressure, low temperature rocks, and only in places the high temperature ones. So that also reflects somehow secular cooling of the Earth. So the model, the petrogenetic model for TTG formation, the TTG stands for tonalite trondhjemite granularite, which are this typical composition of these gneisses that I showed in the first picture. So it's either fractional crystallization of basaltic melt that itself comes from mantle melting. So it goes directly from mantle to tholeite and fractional crystallization. Or it's a two-step story, which is represented here, which first the tholeite crystallized and then remelts or melts in another, in the second time, and then producing a tonalitic magma with cumulate segregation of crystals and liquid that will lead to the full trondhjemite tonalite granularite suite. And cumulate of crystals will be enriched in hornblende, ilmenite, and plagioclase. In which context might this TTG form? So there are two main contexts that are invoked, either an oceanic plateau related to a mantle plume that will lead to a lot of partial melting as the mantle is affected by decompression, thickening of the crust, the oceanic crust, the Mayfi crust, and that we are sitting here on the Deccan Trap, and it's a typical example of that. At some point, this thick Mayfi crust might get thick enough to start to be at the temperature of melting, and it will lead to melting of this tholeite, and that will lead to formation of tonalite. And that somehow will explain for the Archean Proterozoic the association, close association between mafic rocks forming greenstone belts and felsic rocks forming domes in between greenstone belts. The other model, which is more reflecting plate tectonics as active today, is to invoke subduction with burial subduction of oceanic crust that was formerly accreted along the mid-oceanic ridge, and here that will produce calc-alkaline magmas, the same as magmatic arcs. Or at first, according to the composition of the crust during the Archean, it would be the tonalite rather than calc-alkaline. It would be more sodic rich. So what is the main difference between these two models? Well, here it relies on plate tectonics, and this invokes more gravitational instabilities in the mantle. But also, I think, what I insist on here is that here the depleted mantle is directly connected to the mafic and the felsic crust. Whereas here, the depleted mantle is here, and the crust moves here, and there's deconnection between the mafic felsic magmas and the depleted mantle. So this is something to be tested for. So now let's look at the geology. So the oldest rock, well, not the oldest material on Earth is a zircon. You heard of that? This Jekyll zircon is found actually in a sandstone that is a rock that is younger than the zircon that is detrital in it. But this zircon is 4.4 billion years old, which is close to the age of what we think is the age of the Earth. By the way, what did I just say? We didn't date the Earth by dating Earth material. What did I just say? This is the oldest Earth material, and it's almost the age of the Earth. That means that the Earth has not been dated with Earth material. The age of the Earth, the way we think about it, is a concept. It's indirect. It's based on the age of chondrites, meteorites. So on Earth, the oldest material we have is younger than the Earth age, which is kind of paradoxical. and it's contained in a sediment that can be dated at 3.3 billion years, which is 1 billion year younger than the zircon. So the zircon has been traveling for 1 billion years before finding its rest in this sediment. So much has been happening, in 1 billion years. It's a long time. Maybe this zircon has gone through different cycles, several times in the mantle, in the crust, and what happens in 1 billion years? But it tells us that there was early crustal accretion, is preserved in that zircon, and the oxygen isotope signature of this zircon tells us it might have been a zircon from a granite. And a granite, continental crust. So it seems that it's possible to have had continental crust very early in the history of the Earth. But there's no continental scale remnants of that primitive crust, and even though not of that felsic crust, so that probably means that there was efficient recycling and or reworking at that time. So that crust is gone now, at least it's not been dated as such. So either it's been recycled back to the mantle, or it's been reworked so heavily that we don't see the record of that old history. So let's look at how am I doing with time? What time is it? 15 minutes? Okay. So I'll go very quick through that Pilbara craton, but actually not. I'm not going to go through it because it's going to take us too long. But you have very diverse rocks that are different from the ones that we find in the Phanerozoic belts. And I'm just going to insist on here, the slave craton in Canada. The slave craton is equivalent to any other craton made of green stones in green and granitic gneisses in pink. When we look at the geological record of these, they have in the basement complex, in the pink, the granitic gneiss, dates from 4 to 2.8 billion years. And in the magmatic sedimentary sequence, it spreads a bit less, from 2.7 to 2.6. So what does it mean? Does it mean that we have reworking of that old crust for that time period, from 4 to 2.8? Or is it a long history of magmatism over 1 billion years? So in order to, and that's, you see the cross-section, it's over several hundreds of kilometers. So how to explain this long history of magmatism and at the same time over very large surfaces, wide areas? So people have tried, and I'm not going into the details, but there's a continuous record, a geochronological record from 4 to 2.8. It's not like this 4 and then 2.8. It's 4, 3.9, 3.8. There's a continuous record of that. So people have invoked multiple diapirs, mantle plumes, to explain that long-standing high temperature and repeated events, to explain the repeated accretion of mafic and then a slow differentiation for a more mafic to a more felsic crust from green to pink. But it requires also to get rid of the residue because we don't find that residue obviously in the crust. Today it's difficult to identify those mafic rocks that would be the residue after segregation of the felsic one. But I think Nitin mentioned one way to identify this residue without having to get rid of it. Well, at some point it might transform into rocks that are rich in pyroxene and garnet that will look like mantle, although they're probably crustal in terms of petrogenesis. The other way around is to have, in order to explain the widespread magmatism and the long-standing thermal event, is a shallow dipping subduction that goes for very long. That was proposed. Or multiple subductions that are repeating and different places, small subductions. This will explain the widespread magmatism and episodic subduction. And the same type of models have been proposed for the Proterozoic with many subductions or a flat-lying one. This is mechanically very difficult to achieve, but it was an idea. And that would be the first step of magmatic accretion of a lot of mafic crust forming, and then this mafic crust would start to thicken and develop, be affected by partial melting, and develop this dome and synform or basin structures. In any case, if it's for the Archean or the Proterozoic, each segment of crust appears to be recording a single trend of magmatic differentiation from tonalite on sodic magmatism to potassic magmatism. So it seems that it's a single trend of differentiation rather than repeated mafic, felsic, mafic, felsic, mafic, felsic. So I think it's very important, and it's occurring throughout the Archean. So lots of sodic, 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 and then at the end, potassic. So I'm going to take you to a very peculiar place here on the tip of Labrador, which is the place. So I went there with two colleagues from Nancy when I was before I was in Toulouse, and they were searching for the oldest crust on Earth. And here we have probably a remnant of the oldest crust that corresponds to the Ishua crust, which is also one piece of old crust identified in Greenland. And it's called the North Atlantic Craton. Part of it is exposed on Greenland, and part of it on the tip of Labrador. What does it look like? Oh, it's fantastic. Very difficult to get there, but nothing happened to this region since the Archean. The only thing that happened is the opening of that Baffin Bay, or Strait, the Sea of Labrador, and then it was uplifted because on the flank of the rifts and eroded by glaciers. Fantastic for geologists. No vegetation almost. Lots of mosquitoes. Mosquitoes are so much mosquitoes. You wear a thing, and at some point you don't even see because mosquitoes everywhere. That's very annoying. But except on that, you see here the glacial erosion. So you have cliffs, 100% outcrop. Too much, actually. This is one of these glacier erosion, and then you can see here that's been tilted, so you have access to amphibolite facious rocks and granulite facious rocks. I'm going to take you now to this zone here with blue that corresponds to amphibolites, mafic rocks, and salmon that corresponds to felsic rocks. So it looks like that. What do you see in terms of structural position, colors? Black, getting into white, lighter. The black, how is it relative to the, it's on top. And you see the layering here. This is the mafic to felsic crust transition. So what does it look like? You want to know the contact. Okay, here the mafic, it actually looks like monoclinal, but it's actually probably folded several times. It's because it's got a metamorphic fabric. And you have alternation between amphibolite and garnet mica schists. It's metamorphic rocks. These are not sediments and volcanics. So it's been transformed at depth. But you still preserve in some places magmatic textures, coarse textures, fine textures in gabbro's basalt that have not been fully metamorphosed. So this is another example of a gabbro amphibolite transition. This is the garnet mica schist, so sedimentary rocks, very with sillimanite, so it's aluminous rich, which was a surprise to me in rocks of that age, so close to 4 billion years. Other example of that layering of garnet mica schist. Yeah, you need a shotgun for the bears, for the white bears. Fortunately, we didn't have to shoot, but we saw many of them. One at breakfast in a boat. The bear looked at the window and said, "Oh, I want some breakfast myself." So the gabbros, they have preserved some kind of magmatic layering, but there is another layering on top, which is related to leucosomes and melt solid segregation. So you don't want to confuse these two layers. It's not always easy. Huh? I was sure you were going to ask the question, how do we make the difference? It's tricky. And what is fantastic is that in these amphibolites, you have these large ultramafic budins, huge budins. Oh, this is the hammer, and it has a fabric as well. You can see also pyroxene veins that are preserved, with veins like this, cross-cutting. And there's a fabric, and it's then wrapped into the foliation of the amphibolite. So that's probably a piece of mantle rocks. Might be mantle rocks into the mafic rocks. So here's the contact between the amphibolite and the lighter rocks, lighter colored rocks that are quasi-feldspatic. And we see it's gradational. Right. So we go from amphibolite to, how would you call that? Migmatites, is okay? With leucosomes. And what is the connection between these rocks and these ones? Here is the ultramafic budin. So it changed status. It was a budin enclosed in a mafic rock, deformed mafic rocks. And now it's an enclave into a diatic site. So that makes the link between the mafic sequence. And I think from that evidence we can say that the felsic sequence comes from melting of the mafic sequence. And here we have examples of these residual mafic rocks and lots of leucosomes. Other examples. Okay, so I'm going fast across that. And at the end, we get garnet leucogranite and even potassic granite. And that's the last phase of magmatism. And it cross-cuts the migmatites, those potassic feldspar granite. So in these outcrops, over a few tens of meters, we go from sodic magmatism, mafic magmatism, sodic magmatism, potassic magmatism. So the full trend of differentiation is recorded in these rocks. That's a summary of this. So what does it look like? You think, is it more consistent with having, that's not the best, I need to go back, sorry, to discuss that. I should have reproduced that figure, yeah. Do you think it's more consistent with having a mafic crust that transformed by melting into a felsic one, or having plutonic rocks coming from a melting of a subductic oceanic crust that would intrude a mafic crust? In other words, do we see intrusive relationship or gradational contact through high-grade metamorphism? I think it's gradational. No? It's very little evidence for intrusion. There is some motion of the magma, but that only at from the concordant to the discordant veins. No big plutons. So I think it's more compelling with that. So let's finish with a simple model of that to explain this data. Yeah. So the compilation of data on the Archean rocks tells us that in PT, the PT conditions are consistent with that range of temperature for moho depth of 40 kilometers. That leads to a geotherm, Archean geotherm, that will encompass all the pink. So fairly high geothermal gradient compared to today. And we want to also take into account, here we have a number of samples for UPB, a number of samples for neodymium model ages. The green is the age of extraction of magma from the mantle, and the red is the age of crystallization of the felsic magmas. And you see that it covers a large range of time from 3.9 here for the, so it's Pilbara and Barberton, these are two different cratons, but they go from 3.9 to 3.1 for the mafic magmatism, and the felsic one starts afterwards, but it spreads from 3.5 to 2.5. 1 billion year. How do we account for that, for these two observations? So the idea here was to consider a sort of a generic craton with its 40 kilometer thick crust, a 225 lithospheric mantle, with conductivities for the crust and the mantle, and no production of radiogenic decay in the mantle, a production, and then using the surface heat flux. The surface heat flux is the flux that comes from the mantle, is conducted through the lithospheric mantle, and to which is added the heat produced in the crust. And that adds up to the surface heat flux. The surface heat flux today is 45 milliwatt per square meter for most cratons, so that's an average value. So what we did is use that present day situation to extract the heat production in the crust today by decay of uranium, thorium, potassium. So this allows to calculate this, and this number we use it to calculate the geotherm in the Archean, considering that most of the that all the crust was formed in the Archean. And then you can recalculate the temperature this time, considering the heat production in the crust through time. And this is considering only the role of radiogenic decay and the concentration of heat producing elements that goes from very high in the past and that decreased through the Earth history. And you see that's the total heat production, and the heat production related to U-235, U-238, thorium-232, and potassium-40. And what we see here is that the half-life of these elements is very long. It takes a few hundreds of million years, even more for thorium-232 and uranium-235, 238. And these are billion years half-life. In other words, the decay of these elements takes 100 million years to billion years. So how does that translate into the geotherm? So we could recalculate the geotherm 3.5 billion years ago compared to today. And you see here, if I take the granitic solidus to be at 700 degrees, that half of the crust was molten at that time. And more interestingly, that it takes 1 billion years for the geotherm to cool down below with the temperature of the solidus that reaches the Moho. So in other words, we demonstrate here that the crust can remain partially molten for 1 billion years. So we played a bit with the parameters to see how robust was this conclusion. So then it gives us another perspective to interpret the petrologic and geochronological record of Archean cratons. Instead of having lots of mantle plumes, or lots of subduction, it's just an internal thermal evolution of the Archean crust might explain this dynamic, this internal dynamics of the crust with a prolonged thermal event for 1 billion years and ending at the Archean Proterozoic transition. So how do we maintain, or how do we explain the continuous zircon record? And this leads to my last slide, and we propose here that it's related to crustal convection. And that might last as long as the crust is hot enough, it might convect, and the zircons might go up and down, and record dissolution, precipitation, dissolution, precipitation. And that leads to my last with the video. So we try to model that, because that's easy to draw on a paper, right? So now, does it work physically? So at first, so here we have a crust that is 40 kilometers thick, 45 actually. First thermal gradient that is identified by these lines, and think 700 degrees is here, and you'll see the isotherm rising up, temperature rising up, and these are inclusions. That was the big idea, was to put inclusion in there. Inclusions in white are lighter than the ambient material, and the dark ones are denser. And they will be activated just at the time of solidus, so at 700 degrees. Before that, they're not active. So let's see what's happening. Yes, please. Okay, I'll go back. So at first you see segregation of the heavy ones at the bottom and upward motion of the light ones. And that's when that's the 700 degrees isotherm, that's when the 700 degrees isotherm is passed. So you see motion up and down, and that's during sort of we're not at the scale of grains here, we are at the scale of crust. So there's a jump in scale, very, very big jump up in scale. But I think it illustrates the process, maybe that happens at the grain scale, with heavy and light that are separated. And at some point, the layer of low viscosity and high temperature is thick enough to start convection. And then you see that the black ones that were at the bottom are untrained in the subduction with the convection. Sorry, with the convection. And same for the light ones. So that allows for, if you change scale, this might reflect a zircon that was first accumulated at the bottom and then moved again through the convection. And this is to show that I'll show it again. What about this basement? Look for protolith. This is all mixed up. I think it relates very much to the structures I'm used to seeing in these type of terrains, with domes and lots of deformation, polyphase deformation, a mixture of different type of rocks, much more than trying to identify thrusts, localized shear zones, and blocks, which is pretty common still, for people to try to see these. Okay, I think I'm going to leave it here, and I hope it's opened new grounds for you.
Thanks, Oliver. Any questions? So this will be Oliver's last talk.
Yes, I'm going to say just very, I'm very happy to have exchanged with you. I'm going to miss you.